This is our final example of the week. The principles we encountered in the previous examples can also be applied to systems in motion, like this dump truck example that we'll be analyzing. Just note that a full evaluation of a proposed design for a dump truck would involve analyzing various positions of the loading box to ensure that each member and connection can sufficiently support the loads that they will be required to carry. So here's the problem. The box of a dump truck contains 10 cubic yards or 20 tons of hot asphalt, and at a certain moment, the box is in the partially elevated position as shown below. There are joints at A, B, and C, and between points B and C is a hydraulic cylinder. And finally, the diagram is labeled with a bunch of dimensions for reference when we do our calculations. Before we start, I'll set up our positive sign conventions as up, right, and counterclockwise. The first question is how much force must the hydraulic cylinder produce to hold the box in its current position? Remember, this is the hydraulic cylinder, and I'll represent the force as a vector B, just like we did with the tension cables in a different question. Graphically, we can see that the vector B will travel 2 units to the left and 7 units up, so the vector will be -2 and 7. But we need this vector to be a unit vector so that we're only getting its direction. Recall that a unit vector is the vector divided by the length of the vector, so we'll divide -2 and 7 by the length, square root of 7 squared plus 2 squared, or root 53, and then multiply this by B because that's what we're solving for. We'll solve for the force B by taking the sum of moments about A and rearranging for B. So the sum of M about A equals 0 will account for the 20 tons and the vertical and horizontal unit vector components of B. The 20 tons is pretty straightforward. We'll be subtracting it because it acts in the negative clockwise direction, and its normal distance to A is 6 feet, so we'll multiply -20 tons by 6 feet, plus 7 over root 53 times B, the vertical component of vector B, which we're adding since it'll act in the positive counterclockwise direction, times its normal distance to A of 12 feet, plus 2 over root 53 times B, the horizontal component of vector B, which we're adding since it will also act in the positive counterclockwise direction, times its normal distance to A of 7 feet. We can now rearrange for B by grouping these two terms with B in them and then isolating for it, which will give us a force of 8.91 tons for B. Part B asks, what are the reactions at A? This can be solved by performing our basic force balances in the x and y directions. We'll start with the sum of Fx equals 0, which will account for all the forces acting in the horizontal direction. So we'll get Ax minus 2 over root 53 times B, which is again that horizontal component of the vector. From the last slide, we know that B is 8.91 tons, so rearranging for Ax, this will give us a value of 2.45 tons. Next, the sum of Fy equals 0 will account for all the forces acting in the vertical direction. So we'll get Ay minus 20 tons plus 7 over root 53 times B, which is the vertical component of the vector. Again, we know B is 8.91 tons, so rearranging for Ay will get a value of 11.43 tons. On to part C. The question here asks, do the forces on the box satisfy the principle of concurrent forces? Here we have a simplified diagram of the loading box on the dump truck to help illustrate this. From earlier, we know the vertical and horizontal portions of B are 7 and 2, so we get this triangle with a rise of 7 and run of 2. We want to figure out this vertical distance, so to do that we have to scale the triangle up by a factor of 6 to match the 6 feet base. Here's the equation of a slope for reference as to how we're using these values. This gives us a value of 21 feet, but we have to remember to add back 7 feet because the force B is acting 7 feet off the ground, and this will give us a total height of 28 feet. Now we can do the same with the other force. For this one, we'll be using the components Ax and Ay and scaling it up by a factor of 6 to again match the 6 feet base. This will give us a height of 28 feet as well. This means that the forces will intersect at a common point 28 feet above the line, and so the forces satisfy the principle of concurrent forces. And finally, part D of the question is asking us to calculate the loads on each of the three axles if both rear axles carry the same load. Since the loads on the rear axles are the same, we'll represent them with the same variable, and I'll choose W. And for the load on the front axle, I'll designate the variable F. We can solve for the force W by using the sum of moments equation. I'll select the front axle as a turning point. So the sum of M about the front axle equals 0 will account for the 20-ton force and the two identical forces, W. We're neglecting F because we don't consider any forces that act directly on our turning point. Our equation is 0 equals 20 tons, which is being added since it will act in the positive counterclockwise direction, times its normal distance to the front axle of 14 feet, which is this 6 feet plus this 2 feet plus this last 12 minus 6 feet distance, minus W since it will act in the negative clockwise direction, times its normal distance to the front axle of 14 feet, which is this 6 feet plus this 2 feet and plus this remaining 12 minus 5 minus 1 feet distance, minus the other W since it will again act in the negative clockwise direction, times its normal distance to the front axle of 19 feet, which is this 6 feet plus this 2 feet plus this 12 feet minus that last bit of 1 feet. Rearranging and isolating for W, we get a value of 8.48 tons. And to solve for the force F, we can do a simple force balance in the y direction. The sum of Fy equals 0 will account for the 20-ton force, both W forces, and the force F. We just found that W equals 8.48 tons, so we can rearrange and isolate for F, giving us a force of 3.04 tons. To summarize all the parts to the question, we first found the force produced in the hydraulic cylinder B by treating it as a vector and performing a sum of moments about A, giving us a value of 8.91 tons for B. Then we found the reactions at A using our force balances in the X and Y directions, giving us a value of 2.45 tons for AX and a value of 11.43 tons for AY. In part C of the question, we verified our solutions using the principle of concurrent forces and found that the forces will meet at a height of 28 feet, confirming that all three forces satisfy the principle. And finally, we found the loads on the three axles given that the two rear axles carried the same load. Using the sum of moments equation about the front axle, we found that the rear axles each carry a load of 8.48 tons. And through a force balance in the y direction, we found the load on the front axle to be 3.04 tons. This last part tells us that the rear axles do most of the heavy lifting, and the front axles are reserved for steering, carrying a lighter load.